Hello everyone, welcome to Multivariable Calculus and Ordinary Differential Equations. I'm Vamsi, I'm a faculty in the Maths department of IISc. My area of research is differential geometry. This course is meant to be useful for both pure mathematics students as well as students who want to gain mathematical foundations for machine learning, AI, etc., for the theoretical aspects of these things. So let's begin. So most of life is modeled on multivariable functions. For example, if you take the pressure in a room, right? It depends on where you're standing. For every point, you'll have a different pressure, and that depends on 3 coordinates. Linear functions, namely, for example, in one variable, there'll be things like this. Y equals mx. These are functions these functions are the simplest examples of functions possible. I mean, if it was 2 variables, for example, it would have been say 2x plus 3y. This is an example of a function of more than one variable. So linear algebra, the study of linear functions, is like multivariable calculus light. Yeah. So for the first few lectures, in fact, for the first several lectures, more or less, we'll do a reasonably detailed review of linear algebra as well as some topology, some metric spaces. This is not meant as a substitute for actually taking a course in linear algebra or topology. You are expected to know this material beforehand. Yeah. Okay, so let's proceed. So how did linear algebra originate? I mean, like, you remember word problems in high school, maybe say 5 bananas and 10 apples costed like 100 rupees, and 3 bananas and 2 apples 50 rupees or whatever, and find out the cost of each banana, each apple, things like this, right? For example, things like 5x plus 3y is 1, x minus y is 20 or something, right? And we know how to solve them by multiplying this by something and this by something else, adding, subtracting, etc. But to do it systematically, matrices were invented. Yeah, that was the original reason to study matrices, but linear algebra goes much beyond its humble origins. For example, Google's search algorithm or ChatGPT, etc. All of these things use linear algebra behind the scenes. Yeah. All right. So, what is linear algebra? I mean, it's the study of linear equations, but when you say linear equations, you need to tell me what these coefficients are, these numbers, right? In this case, they're integers, but more generally, the coefficients of the linear equations can be, for example, real numbers, complex numbers, etc. Yeah. So, so basically, these coefficients must be from a set where you can multiply numbers, you can add them, and these two behave well with each other. For example, distributivity must hold, and so on and so forth, right? These kinds of sets with these operations of multiplication and addition, recall they're called fields. But if you've not seen fields, not to worry. Simply assume that these coefficients are from real numbers or complex numbers. That's all we'll deal with in this course. In fact, largely real numbers, complex numbers only to a much lesser extent. Yeah. All right. So what is an example of what is a vector space? I won't define it for you, but because I assume that you already know what it is. But whatever a vector space is, the bottom line is you can add vectors and you can multiply by scalars. By scalars, in our case, reals or complex. Yeah. So, and addition and multiplication by scalars, these things satisfy the usual properties that we know. More importantly, rather than recalling the definitions, let's look at some examples. For example, Rn. This is a vector space. I mean, you can take any tuple of n numbers, you can add them by component wise addition, you can multiply them component wise, and so on. Yeah. So this is a real vector space because the scalars are real numbers. Likewise, you have Cn, same thing, except that these Vi's, they're all complex numbers. Yeah. So these are the simplest examples. Here's a more sophisticated example. For example, if you take continuous functions from 0, 1 to R, for instance, continuous functions, and you add them in the usual way. You add functions by doing this, and you multiply by scalars, by real numbers in the usual way. So these things form a vector space as well. Yeah. So for example, polynomials of degree at most n, where n is any integer, with say real coefficients, or even complex coefficients for that matter, real coefficients form a real vector space. What's a non-example of a real vector space? For instance, polynomials of, let's say, degree exactly equal to 2 is not a vector space. Why is it not a vector space? Well, for example, if I take a polynomial like this and take this polynomial, and if I add them up, I'll get a degree 1 polynomial, which is not in the set. Yeah. Okay. So these are some examples. Let's produce a few more examples. For instance, polynomials with integer coefficients do not form a vector space. Do not form a vector space. Okay, but why do they not form a vector space? Because vector spaces need the scalars to come from fields. In other words, the scalars, you must be able to divide by the scalars as well, and if you divide 1 by an integer, this is no longer an integer, right? So that's the problem. Matrices. So if I take, say, m by n matrices with real or complex entries, you can add matrices component wise, you can multiply a matrix entry by a scalar, a number. So that forms a vector space. And lastly, this will be more relevant to us in the second half of the course in some sense. So if I take all differentiable functions from R to R, differentiable functions satisfying a differential equation, these form a vector space. Why do they form a vector space? Please think about it. Okay? All you have to verify is simply that if you add two differentiable functions satisfying these, you get a solution of this equation, and if you multiply them by a real number, you continue to get a solution. Yeah. In fact, many of these examples that we have come up with are in fact examples of subspaces. Subspaces of vector spaces. So for our purposes, a subspace can be simply thought of as simply a subset, subspaces S or vector spaces V, subset that is closed under addition and scalar multiplication. Right. So for example, in some of our previous examples, we looked, for instance, at differentiable functions satisfying a differential equation, yeah? So if I looked at all differentiable functions, they form a vector space in their own right. The functions satisfying these differential equations form subspaces, form a subspace rather. Okay, so here is one more important definition. A set, not necessarily a subspace, a set in a vector space is called linearly dependent. So the word linearly dependent means that there are linear relations among elements of this set if there exists a finite collection of vectors, let's call them x1 so on until xk in S, right? And I'm assuming they're distinct. I'm not repeating these things. And scalars C1 so on until Ck, not all 0. Some of them, at least one of them must be non-zero, such that sum over k, sum over maybe I from 1 to k, Ci xi is 0. Okay? So that's what linearly dependent means. Yeah? So given, here's one more related definition, given a set S, the subspace generated or spanned by S, okay, it's denoted as L of S, is as follows. So you take, basically it's the smallest subspace that contains S. In other words, the definition can be split up into two pieces. If S is empty, the smallest subspace that contains it is 0. Notice that 0 vector must be there in every vector space. A vector space cannot be empty. If S is not empty, then L of S simply consists of all finite linear combinations of elements from S, right? So that's the smallest subspace that contains S. Yeah. One more definition, it can just related to the previous definition. Linearly independent basically means that if the sum of Ck xk is 0, then all the Ck's are 0 for all k. Yeah. So for example, if 0 is in S, the set is already linearly dependent. Why is it linearly dependent? Because 0 is in S, and say for example 1 times 0 is 0, but 1 is not 0. So that means the set is linearly dependent. If S is empty, then this is linearly independent. Why? Because there is nothing to check. It's vacuously so. Okay. Now here is an important little result, if you so will. Again, see, some of these are theorems, if you will. Some of these are definitions. I'm not really making a distinction between all of these because this is prior knowledge. Yeah. So, all right. So suppose if S is a finite collection of vectors, subset of a vector space V, it is independent, linearly independent, if any set of k plus 1 vectors is dependent. is independent, then it's independent any k plus 1 vectors in the span. In other words, if you take the smallest possible subspace, if you take the smallest possible vector space that contains this set S, the smallest subspace containing S, then if this set is independent, that means there are no linear relations among these k vectors. By definition, everything from the span of S is a linear combination of these. So, of course, if you take any k plus 1 vectors, and if that k plus 1 vectors contains these k vectors, then it will be linearly dependent. The non-trivial part of this assertion is if you take any k plus 1 vectors, regardless of whether it contains these vectors or not, it continues to be linearly dependent. All right. So, here is another important definition, that of a basis, right? A set S in V is called a basis if, firstly, it is linearly independent. There are no relations among these vectors. Secondly, it spans V. That is, every vector in V is a finite linear combination of vectors from S. Okay. So, basically every vector can be written using these vectors, and these vectors themselves are linearly independent. For example, here is a rather silly example. I mean, if you take the usual standard vectors 0, 1, 0, 0, 0, 0, 1, etc. These are n vectors in Rn. There are n of them, and they form a basis of Rn. It's easy to see this. I mean, if you take any linear combination of these vectors and if it's 0, then automatically we can see easily that each of these coefficients is 0, and moreover every vector can be written in terms of these. Yeah, so this forms a basis. So, here is another example. 1, 1 and e, pi also forms a basis of R2. And why is that so? Well, you need to prove two things. You need to prove that they are linearly independent. That is, suppose I take C1 times 1, 1 plus C2 times e pi, and suppose that equals 0, 0. Then C1 plus C2 times e is 0, C1 plus C2 times pi is 0, and one of these is not 0. Yeah. So, this would imply, what would it imply? It would imply that either e equals pi or C1 and C2 are both 0. Okay. Why? Because C2e equals C2 pi. So, unless C2 is 0, e must be pi. If C2 is indeed 0, C1 must be 0, and this is of course incorrect. One of them is less than 3, the other is larger than 3. So, it's linearly independent, and if I take any vector, I can write it as a linear combination of these two, and this I will leave as an exercise. Yeah. In fact, in this course, it's a good idea when I say I leave it as an exercise for you to do it immediately, pause the video and do the exercise. Even if I ask a question, and normally I give the answer immediately, but I urge you to pause the video and think about it for yourselves. Yeah. All right. So, so here is one more example. So, if I take 1x and x square, these form a basis for the vector space of, let's say, polynomials of degree at most 2 with, say, for example, complex coefficients. Okay, so this is a complex vector space and this forms a basis. Okay. Now, these are examples. Here is an important result. Okay, this is a fundamental property. Any finite basis of a vector space has the same number of elements. That is, and this number is called the dimension of the vector space. Vector space. Okay, so this is not obvious, this needs a proof, but of course we won't prove it. It's a standard result in linear algebra. So for example, the dimension of Rn is n because we have exhibited a basis that has n elements and every basis has the same number of elements. Okay. One small little point here, right? The dimension of Cn as a real vector space equals what? It is 2n. The dimension of Cn as a complex vector space is n. Okay, so there is a sharp distinction here depending on what scalars you use, real numbers or complex numbers. Okay, so it's very important to keep this in mind. Another important point is not every vector space has finite dimension. Every vector space does not have finite dimension. Can you come up with an example of a vector space that does not have finite dimension? Well, for example, if I take, for instance, continuous functions from 0, 1 to r, continuous functions, this does not have finite dimension. Why? Because these polynomials, they are all linearly independent. If you take any finite linear combination of them and you set them to 0, then all the coefficients must be 0. And they're infinitely many in number, and a finite dimensional vector space can never have an infinite subset that is linearly independent. Why not? It follows from whatever we discussed earlier, and I urge you to think about it. Basically, so what? Right? Please think about this. Okay. So that's a caution. We will largely deal with finite dimensional vector spaces, maybe in the second half of the course when we deal with ordinary differential equations. We'll have occasion to talk about infinite dimensions a little bit, but largely finite dimensions. Okay, right. Okay, so what is the point of linear algebra again? The point of linear algebra is to study linear equations. Yeah, it's to study linear equations, but there is also another point, as we just mentioned, in the context of multivariable calculus. Linear algebra is the study of linear functions, right? A prototypical example being z equals, say, 2x plus 3y, right? So we need to define what a linear function is, right? So that's the familiar notion of a linear map. So a function T between two vector spaces is called a linear transformation or a linear map if T of AV equals A times T of V and T of V plus W is T of V plus T of W. This A is a scalar. For our purposes, as I mentioned, the scalars are usually real or complex numbers, so A is either a real or complex number usually for us. Yeah. So this is a linear map. So in particular, T of 0 is what? It is T of, let's say, 0 times 0, which is 0 times T of 0, which is 0. So any linear map by definition must take 0 to 0. Yeah. So normally we would like to say that y equals mx plus c, this function f of x equals mx plus c is linear. It's not a linear map by our definition. Okay. What is a linear map is mx. This is a linear map if c is not 0. Okay, just a small but important distinction. Colloquially, we say that these things are linear, but by this definition, it's not a linear map. All right, and inductively, from this, you can prove that if you take any finite linear combination, then the same property works for any finite linear combination. Let's say 1, 2, capital N. Okay, this can be proven using induction. Yeah. All right. So we need to study these linear maps in a little bit more detail. Why? Again, because this is the first, this is the 0th step towards multivariable calculus. Again, so the image of a linear map T from V to W, the image is T of V, is a subspace of W. This is crucial. Why is it a subspace of W? Well, what is a subspace? It must be closed under addition and scalar multiplication. So for example, if you take a T of V and you multiply it by alpha by the property of linearity, it's T of alpha V. So this lies in the subspace. Likewise, if you take two vectors and you add them from the subspace, by definition of a linear map, it is this, and this also lies in the subspace, right? Right. So what's an example of a linear map, right? I already gave you one example. More generally, if V is Rn and W is Rm, right? M and N need not be the same. Then, and let's say A is an M by N real matrix, for example. What's an M by N real matrix again? It's it has M rows. Sorry, it has M rows and N columns, right? Sorry, M rows and N columns. Right. So if it has N rows and N columns, then you can multiply. So how can you get a linear map? T from V to W given by T of x equals Ax, right? So x is a vector in Rn, and typically vectors are denoted as columns, right? So if you take a vector as a column vector means it has only one column but n rows, right? You can multiply an m by n matrix with an n by 1 column vector and get an m by 1 column vector, right? So T of x equals Ax is a general example of a linear map. If I were to write it component wise, the ith component of T of x is sum over j aij xj. right? So sum over aij times xj. This is the explicit representation of the linear map. Like for example, more concretely, if I have a map from, I can have a map from R2 to R2 taking xy to, let's say, 2x plus 3y and 5x plus, let's say, 10y or something, right? And this is obtained by using this prescription, okay? This is one example, right? And we'll end by giving one more example. So for example, if I take polynomials, two polynomials of let's say degree at most, let's say for the sake of argument 3, two polynomials of degree at most 3 with say real coefficients, with R coefficients. Here's an example of a linear map. I can take a polynomial and I can differentiate it. Indeed, this is a linear map. Why is this a linear map? Please think about it. Yeah? So we are out of time. Thank you for joining. We'll continue in the next lecture.